Good morning, everybody. We created a wireless power system based on strong magnetic resonant coupling. Our project is based on the principle that two objects resonating at the same frequency can effectively exchange energy. Also, a hybrid metasurface is being implemented to redirect the magnetic field from the transmitter to the receiver.
The main interaction of the system occurs between the transmitter and the receiver coils. The transmitter coil is excited by the driver loop, and this interaction works similar to the step-up transformer to increment the magnetic field. Then the receiver coil can intercept this change in magnetic field and will generate an EMF. Then the load loop will work as a step-down transformer, and it will be connected to the load. The other purpose of the driver loops is to help match the impedance of the system to get the maximum power transfer.
So in order to understand what's going on with the components, we use S parameters. We obtain the reflective coefficient S11, and then from there we use the transfer function by using KVL so that we could obtain the transmission coefficient S21. And then the other parameter that we needed to find was the coupling coefficient, which from there we use the Newton's formula so we could find the mutual inductance. From there, we were able to use MATLAB and PSpice for simulations. And then for here are some simulations that we ran during the time we had, and then our main parameter is K23.
So we will different set of coils for testing purpose, and we get our best results with a set of coil working at 16.93 megahertz. Although we cannot use this frequency, therefore, to comply with the ISM regulation, we build a set of coils to work at 13.56 megahertz. And after testing, we measured that the maximum power transfer for this set was at 22 centimeters.
Based on the measured values of the components, the coupling coefficient, and having the transfer function, we were able to simulate, we were able to write a script on MATLAB to run the simulation. This would give us we vary the input frequency and the coupling coefficient. With this, we would get the expected behavior of the system. I said the backwards, sorry. But
Our hybrid metasurface will have unit cells with negative and close to zero permeability. The permeability parameter is what dictates the new direction of the magnetic fields once it passes through the metasurface.
Right. Then we built an inverter so we can drive more power into the system since we needed to charge smart devices or for us to use it commercially. Then simulating, we were able to get the maximum power point where we were able to see that 23.9 centimeters was our simulated point, and we got our measured value to be 22 centimeters. Any questions?
What is the efficiency you achieve?
I'm sorry, what?
What is the efficiency?
Okay, we get an approximate efficiency of about 40%. But since that's an approximation, because for measuring the current, we don't have the current probe to work at that can work at 13.56 megahertz. Then we use like LEDs to see what's the difference. How many LEDs light at different power. First, we just test the LEDs without the antennas, just to see how it lights depending on the voltage and the power. And then from there, we derive the approximation on this about 40% of efficiency. But we can show you more about that on the demonstration.
And one more question: did you think about the radiation and EMC, because we got far apart, so you're gonna have a lot of leakage around. So did you think about EMC perspective also in this case?
So that was what we were hoping to direct it more with the metal materials. Currently, we're still researching how directively it would work with the ones that we have designed currently.
Why does the system use intermediate resonant coils?
What is?
There's 4 coils in the system.
Yes.
What are the intermediate coils there?
Okay, that's our from transmit and receive coils. First, the driver loops is just to excite the coils, so the transmitter can increment the magnetic field, and it will send to the receiver. And then the other loop, the other load loop will decrease the power to can be connected to a load.
Are you transmitting enough power to, say, charge a phone that's 8 inches away from your...
Yes, what we are trying to do is be able to charge small devices. So once we reach the critical coupling point with before smaller than 0.01, it can have a wide range to charge. So for example, we can, from one of our testings, we get results that it works from 50 centimeters up to 90 centimeters. And so it can charge at that distance. So if we place the device in the middle, like in the rounded tables, we can place the device in the middle, so everyone around the table will be in that range, so we can the devices can be charged at that point.
So what's the biggest advantage you have over the existing wireless charging system?
So currently, mainly people are using inductance, and as the biggest company, Apple, tried to create a pad that could charge multiple devices, like let's say 3 phones in one pad. However, they couldn't achieve it because of heat dissipation. So we were hoping that since we aren't directly on top of a component, we can spread out heat dissipation more, and then we could all communicate. So to achieve their goal that they wanted to do.
Thank you.